Hi and Assalamualaikum to Sir Sheikh and my classmates. Before I begin, let me introduce myself and my group members. My name is Nur Alisa binti Anwar along with Fatimatul Akmal binti Mas'ud and Nur Amira Najwa binti Mahdir. We are from Group 1 and today we are going to present and explain about Chapter 5, which is Mechanical Properties of a Materials. Woo! First of all, let me introduce about stress and strain of a materials. What is stress? Stress is defined as a force applied per unit area. The formula of stress, which the stress is equal to force that are perpendicular to its object, divided by cross-sectional area of force application. It expressed in pounds per square inch or pascals. There are different types of stress, which are shear stress, tension or tensile stress, and compression stress. The shear stress is defined as a direct stress that pushes one side of a body material in one direction and the opposite side of the body of material in the opposite direction. The shear force are pushing in opposite ways and cause a material to bend, slide, and twist. Next, compressive stress is direct stress that push material together. The compressional force push towards each other. Last but not least, the tension stress refers to the direct stress that pulls material apart in positive direction. The tensional force pull away from each other. Next, what is strain? Strain is defined as the change in dimension per unit length. Here is the formula of the strain, which is the change in length is divided by its original length. The unit of strain are in per in or meter per meter. So, in this slide, I will be talking regarding on the elastic deformation. In modulus of elasticity or Young's modulus, stress and strain are linearly related in elastic regions, which is Hooke's law. Here is the formula of modulus of elasticity, which the stress is divided by strain. Besides, when the bonding strength is higher, the modulus of elasticity will be higher. After that, I will explain about hardness of material. Hardness can be defined as resistant to permanent deformation of plastic or indentation or resistant to scratch. The harder the material, the greater the wear resistance. Besides, indentation is one of the common techniques to observe the hardness. Indented material depends on what test that did you apply. Indented material is usually a ball, pyramid or cone, which is made of material is much harder than the material have been tested.
There are several types of hardness. Firstly is work well. It is quick and cost-effective process, but no specimen preparation is required. Secondly is brittle. The process is slow when compared with work well. The test cycle takes between 30 and 60 seconds, and each specimen surface can be rough. Besides that, for brittles, the process is rather slow and also takes between 30 and 60 seconds, but the specimens need to be prepared. Last but not least is noob. It's same with brittle and brittles, where the process is slow and the test cycle takes between 30 and 60 seconds, but for specimen, it should be polished.
Assalamualaikum, my name is Fatimatul Akmal. So, I will explain about fracture. What is fracture? Fracture is separation of a solid under stress into two or more parts. There are two steps of fracture. First, formation, and second is propagation. On this slide, there are two types of fracture, which are ductile and brittle. For ductile, metal occurs after extensive plastic deformation and is categorized by slow crack propagation. It can be found most metals which not too cold. Extensive plastic deformation ahead of crack, which is slow crack propagation. For ductile, it do not break immediately. Brittle proceed along characteristic crystallographic plane called cleavage plane and has rapid crack propagation. It can be found ceramic, ice, cold metals. There are no applicable plastic deformation break the end of elastic limit with fast crack propagation. For brittle, it breaks without warning. For this slide, it shows 5 stages of ductile fracture. First, necking. Second, formation of microvoids. Third, coalescence of microvoid to form a crack, which many microvoids occur that cause crack. Fourth, crack propagation by shear deformation. And lastly is fracture.
For ductile, it produces one piece and there are large deformation. However, for brittle, it produces many pieces and small deformation.
Fatigue is a failure mechanism that involves the cracking of materials and structural components due to cyclic or fluctuating stress. Estimated to cause 19% of all failures of metallic structures such as bridge, aircraft, machine components, and so on. Fatigue failure is brittle-like and relatively little plastic deformation, even in normally ductile materials. Besides that, applied stresses causing fatigue may be axial, which is tension or compression, flexural, which is bending, or torsional, which is twisting. Fatigue failure proceeds in 3 distinct stages. Firstly, crack initiation in the areas of stress concentration. Secondly, incremental crack propagation. And thirdly is final failure, even catastrophic rupture. For first stage, crack initiation. Fatigue cracks almost always initiate at a free surface and near a stress visor. For example, the toe of a weld. The initial development of a fatigue crack occurs at localized discontinuities in the metal's crystal structure. For second stage, crack propagation. Once a crack is initiated, continued cyclical stresses repeat the process, slowly growing the microcrack, which becomes a threat to structural integrity. For the last stage, is for the final failure event. For example, catastrophic fracture can be ductile or brittle depending on the material, thickness, temperature, and the applied stress. Fatigue failure typically occurs suddenly. This is a fatigue properties of material SN curve are tested in rotating bending test in fatigue testing apparatus that shown in the slide, and result is commonly plotted as S stress versus N, which is number of cycles to failure. The SN curve exhibits 2 distinct behaviors for materials. For the figure 1, curve showing a fatigue limit. Fatigue limit, which is endurance limit, occurs for some materials, for example, ferrum and titanium alloys. In this case, the SN curve becomes horizontal at large N. The fatigue limit is a maximum stress amplitude below, which the metal never fails no matter how large the number of cycles is. For the figure 2, curve does not show a fatigue limit. The relationship for the latter curve shows the number of cycles a metal can endure before failure for a range of applied stress levels. In general, metals can sustain high loads for a low number of cycles, for example low cycle fatigue, or they can sustain low loads for a large number of cycles, for example high cycle fatigue before failure. There are two factors that affect fatigue life. Firstly is magnitude of stress, which is mean, amplitude, and so on. Secondly is quality of the surface, such as scratch and sharp transitions. There are several solutions for fatigue. Firstly is polishing. Polishing means remove machining flaws. Secondly is introduce compressive stresses. There is composite for applied tensile stresses into thin surface layer by short pinning. Short pinning is a very small shot into surface to be treated. And lastly is case hardening. It makes harder outer layer and also introduce compressive stresses.
That's all from Group 1. Thank you.